Today we are on page 3 of our chapter 3 notes packet, section 3.3, which is simplifying radicals. To simplify a radical, these are the steps we're going to follow. We're going to express the radicand as a product of factors. The largest perfect square, cube, or n factored, followed by the non-perfect square, cube, or n factors. We're going to find the root of the perfect factors from A. This is the coefficient of the radical answer. And the B part is the radicand of the radical answer. Now keep in mind our perfect squares: 4, 9, 16, 25, 36, 49, 64, 81, 100, and so on. You need to also know your perfect cubes. Perfect cubes are 8, 27, 64, right? 2 cubed is 8, 3 cubed 27, 4 cubed 64, 5 cubed is 125, 6 cubed is 216, 7 cubed 343, 8 cubed 512, 9 cubed 729, and 10 cubed 1000. Other powers you should be familiar with: 2 to the 4th. 2 to the 4th is equal to 16. 3 to the 4th, that would be 81. 2 to the 5th, well, that's 16 times another 2 is 32, and 2 to the 6th is 64. Now to simplify the square root of 50, we're going to factor 50 into perfect square part. The largest perfect square that is a factor of 50 is 25. So we write 50 as 25 times 2. I'm always going to circle the perfect factor. Okay. Out comes its square root, that would be 5, and then the square root of 2 remains. So 5 square root of 2. Number 2, the square root of 700. We'll express 700 as 100 times 7. 100 is the perfect square. Its square root is 10, so 10 square root of 7. Number 3, the square root of 72, xy to the 4th. 72 can be factored into 36 times 2 times x times y to the 4th. 36 and y to the 4th are our perfect squares. Square root of 36 is 6. Square root of y to the 4th is y to the 2nd. And the square root of 2x remains. Number 4, 32x to the 5th. We're looking for the square root of 32x to the 5th. 32 will break apart into 16 times 2. What part of x to the 5th is a perfect square? X to the 4th. Remember, the exponent would have to be a multiple of 2. So we'll break x to the 5th down into x to the 4th times x. Circle our perfect squares. Take their square roots, 4x squared, and then the square root of 2x remains. Number 5, cube root of negative 512 x to the 5th. Well, negative 512 is a perfect cube, so that just stays. X to the 5th, again, for the exponent to be a perfect cube, the exponent would need to be a multiple of 3. So we'll break x to the 5th down into x to the 3rd times x squared. I'll circle our perfect cubes. Negative 8x cube root of x squared. Number 6, the 4th root of 16x to the 5th divided by 81 y to the 16th. Okay. Well, 16 is a perfect factor. X to the 5th, what piece of it is, x to the 4th is, so we'll break x to the 5th down into x to the 4th times x. And the denominator, 81, and y to the 16th are perfect factors. Circle our perfect factors here. take their fourth roots. So this would be 2x. The fourth root of x remains over 3y to the fourth. Number 7, we're looking for the nth root of x to the an. Okay, so this is the nth root of x raised to the an. That means x raised to the a times x to the n. So x to the n is our perfect factor. The nth root of x to the n would simply be x, and then the nth root of x to the a remains. Number 8, 2 times the square root of 50b to the third. So 2 square root of 50b to the third. 25 times 2 is 50, and b squared times b are the perfect square factors of b to the third. Circle our perfect squares. Bring down the 2. Square root of 25 is 5. Square root of b squared is b. And then the square root of 2b remains. And we multiply 2 times 5b is 10b. Square root of 2b. Number 9, the square root of 0.2. Now this is interesting. Well, there's more than one way to do this. Maybe we'll save this for tomorrow in class. We'll save that for tomorrow in class. It's important to note, a simplified radical cannot have a fractional radicand. Also, a denominator may not contain a radical. If a radicand is a fraction, multiply the numerator and denominator by the value which will make the denominator a perfect square, cube, or nth power. Then take the root. Okay, so our focus is here that we cannot have a fraction in which the denominator contains a radical. All right, so if we focus on the denominator, I see that 9's a perfect square, right? And a to the third is not perfect. So we need to bring it up to a perfect square. So if we multiply by a, when we do the denominator, we need to do the numerator. Then we'll end up with the square root of 10a over 9a to the fourth. Okay, now take our square roots of our perfect squares. We have square root of 10a remains as a numerator, but now the denominator, its square root is 3a squared. So a radical in the numerator is okay, but not in the denominator. Let's look at number 11, which starts out as 3 times the square root of 5a to the 7th over 9b to the 7th. Again, our focus is on what's called rationalizing this denominator. 9's a perfect square root, has a square root, but b to the 7th is not a perfect square. So if we multiply by b, so we're actually multiplying by 1 in the form of b over b. So we'll have 3 times the square root of 5. Now when I write 5a to the 7th, I'm going to write a to the 7th as its perfect square factor of a to the 6th times a times b over 9b to the 8th. Bring down the 3, circle my perfect square factors. Out come their square roots, so this would be the square root of a to the 6th. Remember, divide the exponent 6 by 2. That'd be a to the third. The square root of 5ab remains over square root of 9 is 3, square root of b to the 8th is b to the 4th. And we have one more step here, right? we need to simplify. These 3's can divide out. So we have a to the third square root of 5ab over b to the fourth. Number 12, this is cube root. Cube root of 16, x to the fourth, y to the fifth. And concentrate on that denominator. If we brought y to the fifth up to y to the sixth, so let's multiply by y. And as I write 16 x to the fourth y, I'm going to break it down into its perfect cube root factors. Let's see, 8 times 2 would be 16, times x to the third times x would give us x to the fourth, and then y over y to the sixth. Circle our perfect cubes. Out come their cube roots, 2x, cube root of 2xy remains under the radical over y squared. And lastly, number 13. More than one way to do these at times. For number 13, yes, we could just divide right there because, yes, 15 divided by 3 would be 5. And then we would just have to worry about the x here. Let's suppose we didn't notice that, though, and let's suppose we simply multiplied by 3x, right, to bring this up to a perfect square in the denominator. And then we would have 45x to the third times y. Well, 45, the x to the third, I'll leave it as square. I'll leave it as x squared times x, and then times y. Over, this is 9x squared y squared. Now notice, though, the 45 we can simplify into 9 times 5. So let me try to squeeze this in over here. Circle our perfect squares. And we get the square root of, not so large. This is 3x should be on the outside. Let's fix that, 3x, and then the square root of xy remains. Hope you caught that. I need my 5. Okay. So the square root of 5xy remains. All over 3xy. And one more simplification here. The 3's divide out, and so do the x's. Now that's just the lights going out in the classroom, so no motion. So it looks like we have an end result of the square root of 5xy over y. And this concludes our video for tonight.